So I don't think anybody noticed, but in lesson 5.6, when I was first covering separable differential equations, I left out a specific kind of problem. I left out any problems that involved natural logarithms. And it's because natural logs do something interesting to these separable differential equations. I think the best way for me to show you what happens is through an example. But before I get into that example, I want to remind you about a property of exponents. So for example, think about something like e to the x plus c. The point I want to make here is that there's something interesting that we can do to simplify this. In particular, I want to mention that we could write this, if we wanted to, as e to the x times e to the c. Now, you might think that's weird and unnecessary, but it turns out it's going to be really, really vital for some of the stuff that we do today. So I just want to make sure that you're clear on why it is that this can turn into this. And the idea is really simple. You guys are used to seeing this go backwards, actually. If you have two things that have the same base, we know that we can add the powers together. So we know that when you do this, you get this. What I'm going to be asking you today is, when you see something like this, when you see two things added in an exponent, know that if you want to, you can separate that out into two things. The reason for that will become clear in just a couple minutes. So I want to go straight into an example here. Let's find the general solution to the differential equation y prime equals 4xy. So hopefully you remember the steps from yesterday. The steps for this should be, step 1, rewrite as dy dx equals 4xy. Step 2 was then multiply by dx, so that gets us dy equals 4xy dx. Remember, doing that effectively declares this side to be the x side of the equation, and this to be the y side of the equation. And so now that we've done that, we know that we need to separate things, right? On this right side, I want to see only x's. On this left side, I want to see only y's. So the only thing that's out of place is this y. So if I divide both sides by y, I'll end up with dy over y equals 4x dx. I've now separated variables, right? Step 1 was to write as dy dx. Step 2 was to multiply dx over. Step 3 was to separate variables. And now step 4 is actually to take the antiderivative of both sides of this equation, because I can, now that the variables have been separated. I'm recording this during the lunch, which means the PA is going to come on from time to time. I will try and pause without hearing people's names. So I'm sorry, I just left off saying we were going to take the antiderivative of this. The integral of dy over y, that's basically, if you think about it, this integral here is basically the integral of 1 over y dy. So the left side of this is the natural log of the absolute value of y. On the right side, the integral of 4x is just 2x squared plus c. And this thing right here is, in some sense, the general solution. It's not my favorite. It can be simplified, and the simplification makes it look really, really neat. I'm going to do something interesting here. I'm hoping that you guys remember from, I think it was the 5.B, maybe it was the 5.A lesson, this idea that if you have the natural log of something, that's a terrible A. If you have like the natural log of A equals B, we can rewrite that and say that e to the b power has to be equal to a. I'm going to do that right here. I have the log base e of y equals this whole thing. These are the same thing. A is y, b is 2x squared plus c. So I'm going to rewrite this as e to the 2x squared plus c equals y. And the reason I'm interested in doing this is that I can actually get my answer to look like y equals. This will be really neat. So I'm just going to rearrange this to make it prettier. Y equals e to the 2x squared plus c. But then think about that review comment that I made at the beginning of this video. I said if you have an exponential function that has two things added together, I could separate this out to be y equals e to the 2x squared times e to the c. And now here I'm going to do something really sneaky that's probably going to bother some of you. Remember, what is c? C is just it's the constant of integration. It's a constant that we don't really care what its value is. It's a constant. So what happens when I take e and raise it to the power of some arbitrary constant? Isn't this thing just some other c? We could call it c2 if we wanted to. If we did that, I could write my answer as y equals c e to the 2x squared. I could put a c2 down here. It's not really necessary. This is actually my favorite answer to give for this. I think it's really neat that we can do that. And it probably reminds you guys of something. I hope it kind of reminds you of PERT. And I'd like to go through an example of that right now. So I'm going to move into the next slide and we're going to take a look at this. Suppose that you had a differential equation that looked like this, something written in words. It says the rate of change of the population of an ant colony P with respect to time t is directly proportional to the current population of the colony. So based on last night's homework, we should be able to write this as a differential equation. So first, the rate of change of the population of a colony with respect to time t, that means dp dt, that is directly proportional to, so equals k times, directly proportional to the current population. Well, the current population is p, so k times p. Right? Now let's take a look at solving this thing. Right? Well, the first step is to multiply by dt. Right? So I'm going to have dp equals k p dt. Now the next step is to separate variables. And remember, the variables here are t, this is the t side, and the other variable is p, this is the p side. Anything that's not t or p is a constant. So in this problem, what's the constant that's sort of staring at us? The constant we're looking at is k. So k, I'll just leave here with the t side. I'm just going to move the p over. This will give me dp over p equals k dt, right? So at this point, I've separated variables. Step 3 is to take the integral. I'm going to do the integral of dp over p equals the integral of k dt. On the left-hand side, the integral of dp over p, that's the natural log of p, because it's 1 over p. And now this is interesting. What's the integral of k dt? And I'd recommend you pause and think about this for a second. K is a constant. T is the variable, right? Your answer should not be 1/2 k squared. If that's what you thought of, then think about it again. I might encourage you, think about something like 3 dx. Isn't the integral of 3 dx 3x? Plus c. The integral of k dt should be k t plus c. Now, at this point, I'd almost encourage you to pause the video and see if you can solve this thing for p. Right? Use the steps we did in the previous problem. So I'm hoping that you just did that, and you got e to the kt plus c equals p. Right? So if I switch this around, p equals e to the kt, and I'll even skip a step here. What do we do when we have things added in an exponential? We can make it e to the c. Right? But we mentioned previously that e to the c is just some arbitrary constant, so I get p equals c e to the kt. And the point I want you to understand, that's literally the same thing as PERT. I'm just using different letters for things, right? If I had instead written it as, a equals p e to the rt, notice that the shape of this thing is the same as the shape of this thing, right? So I'm drawing to the close of this lesson. The point that I wanted to get at is basically any time that you end up with a differential equation that has dp over p or dy over y, something like this that yields a natural log, I want us to be thinking about how we can rewrite that and effectively end up with an exponential that doesn't have plus c but rather has times c. In the next video, I'm going to go into a little bit more detail about where this differential came from and how we solve these sorts of things, but that's the end of this video.